Hi folks, so let's start with chapter 0 of Hatcher. My main goal for this video is to introduce homotopy equivalences. All right, so first some notation. This blackboard bold 1 will denote the identity function from a set to itself, often from a topological space to itself. And by a map F from one topological space X to another topological space Y will mean a continuous function. So preimages of open sets are open. All right, so I like to introduce homotopy equivalences between spaces by first comparing them to homeomorphisms between spaces, which is a concept you might have heard before. So if X is a space and Y is a space, often you define a homeomorphism between them as a single function F that's continuous, so it's a map, and you want F to be a bijection and to have a continuous inverse. An equivalent way of doing that is giving yourself two functions, f and g, and we want both f and g to be continuous. We want them both to be bijections, and we want f and g to be inverses of each other. So one way of saying that is if I first do f and then do g, I get the identity map on the space x. And if I first do g and then do f, I get the identity map on the space y. Okay, so if you have maps F and G satisfying these conditions, then the spaces X and Y are homeomorphic. Their homeomorphic spaces are denoted by one of these three symbols. I mean, equality is used just because to a topologist, homeomorphic spaces are really the same. Now, why did I call G, the map G, why did I call it G instead of F inverse? Well, that's because I'm previewing the definition of a homotopy equivalence between spaces. So the maps F and G, again, going from X to Y and back, those are homotopy equivalences if one composition, F followed by G, is not equal to the identity on the space X, but it's homotopic to the identity on the space X. And similarly, G followed by F is homotopic to the identity on Y. So the big disclaimer here is that we first need to define homotopies between maps before I can define homotopy equivalences between spaces. So I'm leaving that yet undone for right now. But if you have two maps F and G, and the composition maps are homotopic to the relevant identity maps, then we say that X and Y are homotopy equivalent spaces, denoted X homotopy equivalent to Y. All right, so homeomorphisms between spaces, they're essentially identical spaces. If the space has a dimension, then the other space has the same dimension. So here a sphere and this wobbly sphere are both two-dimensional manifolds. Homotopy equivalences between spaces can, for example, change dimension. So this circle is a one-dimensional space that's homotopy equivalent to this two-dimensional annulus. They still have the same number of one-dimensional holes, though, both a single loop. So to find maps achieving this, I could take F to be the inclusion of the circle to the inner ring of the annulus. And I could take this map G to be the contract map that maps each of these colored segments to single points. So this red segment maps to this red point, this yellow segment maps to this yellow point, and similarly all the way around the annulus. So one composition is actually equal to the identity. So if I do the map F and then the map G, I include this circle into the annulus, shrink the annulus back down to the circle, I just get the identity. So in this case, this composition would be equal to the identity on space X, which is certainly a homotopy equivalence. But the other composition is not equal to the identity on Y. If I do G and then F, I take the annulus, shrink it down to the circle, and then include the circle back in. That's not the same thing as the identity on Y, although it is a homotopic map. Okay, So homeomorphisms between spaces are it's the simplest notion of equivalence between spaces. Homotopy equivalences is a relaxation thereof. Okay, now more spaces can be deemed to be equivalent using homotopy equivalences than before. The circle and the annulus, for example, are homotopy equivalent, even though they're not homeomorphic. All right, so I owe you a description of what homotopy equivalences between maps are to complete this definition. So to define a homotopy equivalence between maps, we'll do the following. Capital I is going to be the unit interval from 0 to 1. And we say that two maps, F0 and F1, from space X to space Y, are homotopic, denoted F homotopic, F not homotopic to F1, if there's a map capital F, not from X, but X cross the interval to Y, such that if you restrict capital F to time 0, you obtain the map little f0. And if you restrict the map capital F to time 1, you obtain the map little f1. So in pictures, X might be a circle, Y might be this gray square with two holes removed, and F naught might map the circle in as this red loop, and F1 might map the circle in as this blue loop. And then it seems like you could sort of deform the red loop to the blue loop inside the space Y. And to make that rigorous, we consider this map capital F from the entire cylinder, the circle across the interval in. And as we sort of scroll from the left to right in the cylinder, we get deformations of this map where I go from the red loop to the orange loop to the yellow loop to the green loop to the blue loop in a continuous way, deforming from the map little f0 in red to the map little f1 in blue. All right, so that's a rigorous concept, rigorous definition that matches our intuition of deforming one map to the other. So a piece of notation, we started with map little f naught and little f1, but in between I talked about all these interpolating maps, little ft, and these maps are defined by looking at time t from the global map, capital F. All right, some notation that'll come up later, or some language, is that we say that a map F is null homotopic if it's homotopic to a constant map, a map shrinking the entire space to a point. So in these pictures, neither the map F0 nor F1 are homotopic to a constant map, because I can't shrink them past the hole that they're wrapping around the map to a single point. Another concept which will come up later is homotopies relative subsets. So if A is a subset of our domain space X, and if all of these interpolating maps fix A, then capital F is a homotopy relative A. So by fixing A, we mean that where a point in A gets mapped is independent of the time in this deformation. So as examples of that, here I have, these are pictures from Hatcher's book, Algebraic Topology, which we're going through. This is a picture of a Mobius band, and I could imagine taking the identity map from the Mobius band to itself, but deforming it to be a map that sort of shrinks in along these light segments and maps the rubber band down to its central core. So that would be a homotopy from the identity map on this Mobius band to a map that just maps to the central core. And I could do the same for each of these three spaces. I could homotope from the identity map from this figure-8 space to itself down to a map whose image is only this barbell shape or this figure-8 shape or this sideways theta shape here. Okay, so this is the notion of homotopies between maps. Two maps are homotopic if you can deform one to the other using a larger continuous interpolating map defined on not X, but X cross the interval. Let's go back now and complete our definition of homotopy equivalence between spaces, which relies on the notion of homotopies between maps. So these two spaces, X the circle and Y the annulus, are homotopy equivalent spaces because I can define two maps F and G. F just includes the circle into the inner ring of the annulus. G shrinks the annulus down to the circle by mapping, short segments on the annulus down to points on the circle. These two maps show that the spaces X and Y are homotopy equivalent because the relevant compositions are homotopic to the identity maps. So if I first do F, include the circle in, and then do G, shrink the annulus back down, that maps every point on the circle to itself. This is an identity on the nose. Nothing to do here. But if I first do G, shrinking the annulus down to the circle, and then include the circle back in, according to F, then I haven't done the identity on the annulus. However, first doing G and then F is homotopic to the identity on the annulus. And here's the picture of that. So I have the annulus cross the interval. That's my picture right here. And then at time 0 in red, I do the identity map. At time 1/2 in green, I shrink the annulus halfway down onto the inner circle. And then at time 1, I have this annulus in purple that I shrink all the way down to the inner circle. So this map capital H is a continuous map from the annulus across the interval to the annulus. And at time 0, it gives you the identity map on the annulus. And at time 1, it gives you this composition of G followed by F, which is shown in purple, mapping the annulus to this inner circle. So that is the homotopy between maps, showing that this composition G followed by F is homotopic to the identity map on Y. Therefore, finally proving that the circle and the annulus are homotopy equivalent. All right, so I'll end there. I hope you have a better understanding now for homeomorphisms between spaces, which maybe you've seen before, and homotopy equivalences between spaces that we defined using homotopy equivalences between maps. Thanks.